Hello everyone, and welcome to Night School. Steel construction from the mill to topping out. Today is December 3rd, 2018, and this is Session 7, Field Fixes and Solutions, presented this evening by Dr. James Fisher. My name is Brent Liu. I'm with AISC's Continuing Education Group, and I will be moderating this evening's presentation. I want to introduce this evening's speaker, Dr. James Fisher, Vice President Emeritus of Computerized Structural Design in Milwaukee. Jim Fisher received his bachelor's degree from the University of Wisconsin and his master's and PhD degrees from the University of Illinois. Dr. Fisher's structural expertise has resulted in authoring and co-authoring 16 books and numerous technical publications, and he has lectured for AISC throughout the United States as well as Mexico. Dr. Fisher served as the chairman of the AISC Specification Committee for 7 years, and he continues to be active on several AISC task committees. He's an emeritus member of the AISI Cold Form Specification Committee, and additionally he serves as a consulting engineer to SJI, the Steel Joist Institute. Dr. Fisher received many awards from AISC throughout his career, including the T.R. Higgins Lectureship Award, the AISC Lifetime Achievement Award, and the J. Lloyd Kimbrough Award, AISC's highest honor. Jim, thanks for being here, and I'll hand things over to you.
Thank you, Brent. Good evening, everyone, and maybe good afternoon or late afternoon to those of you on the West Coast. As Brent says, we're going to talk about field fixes and solutions. Certainly not all the things I've encountered throughout my career, but many of the items that I have encountered through many years of practice. As Brent says, this is the second to last presentation, and there'll be one more on December 10th, Quality Control and Quality Assurance, presented by Larry Kruth, who's Vice President of Engineering with AISC. What we're going to talk about this evening are, first of all, a couple of slides on what to do when notified about a field problem. We're going to spend a considerable amount of time on anchor rods because it seems like through the years, at least my experience, and I know with other engineers, that's something that happens frequently, far too frequently, are anchor rod problems. We will also discuss columns and beams and fixes for those, reinforcing members and connections, fit-up problems, and then we'll conclude with a discussion of some member selection guidelines. Now, what to do when notified about a field problem? I think the most important thing is to make sure you have accurate information. If you don't have accurate information, you can waste a lot of time. So photographs, telephone calls, you need the information, especially if you can't get to the job site if it's some distance away from you. Act immediately to avoid any delayed charges. Whether you think you did something wrong or didn't do anything wrong, it's important that you jump in and help so that the delayed charges are minimized. Next, try to determine the cause of the problem. Is a fix required? I mean, lots of times you can, as we used to say, sharpen your pencil. You may find that you don't need a fix. And parens there, if no money is spent on a fix, then there'll be no argument as to who pays for such a fix. Think primarily about labor costs in fixes. Materials cheap. The cost of doing the engineering, the cost of to the erector, fabricators in doing the fixes, their labor is far more expensive in general than the material. Before you embark on all your studies and solutions, discuss what paperwork is going to be necessary with the owner, architect, fabricator, erector, etc., to make sure they are all satisfied so that everybody can sign off on the fix. And we engineers are often too afraid to talk about our fee and how it will be paid. I think it's important that you discuss the fact that, you know, everybody else is going to get paid for this fix, and engineering is an important part of it. And of course, the finer job you do as engineers, probably the least cost the fix will be. So don't be afraid to discuss your fee and how it will be paid. Quite often, fixes are proposed by the steel fabricator or erector. They often have encountered things that you may not have encountered. So listen to them. They may have some really great ideas. If their ideas actually won't work for the condition at hand, fine, you can't use it. But if you can, it may save some money, as they have their favorite things to do, and it can be helpful to go along with their suggestions. While you study that slide, we'll start talking about anchor rod problems. As you can see from the slide, there are no anchor rod problems with this project. I don't know to this day if there are anchor rods or whether this building hasn't flown away, but that is a very elaborate foundation system that you can see. They already have the roof on and one wall is sided, so I don't know what's going on, but it's unique, so I couldn't resist that as a lead-in slide. So sometimes there are problems due to erection and construction sequence, and you can see from this slide, if, for example, the walls are up, the concrete walls or masonry walls, and then you go to set the steel, there are anchor rods which one cannot reach. So you may have to hold the column until it's stabilized for erection. As you know, OSHA has requirements for the number of anchor rods, being 4, and if you can't get a couple of them in, then you need to take action to make sure that the column is stabilized. So that's all a matter of sequencing. This is also one of my favorite slides. This condition, I think they were 40-foot high HSS columns. This building was in Utah, and it collapsed during a little wind event. I think the wind was roughly 30-35 miles an hour, but the erector had one of the joist girders on this job just sitting on top of a column, and the folks went to lunch. A little wind came up, girder slid off the top of the column, and it was attached to the adjacent column, so it fell down. The interesting thing here is when most of these collapses occur, the anchor rods break, and they don't usually tip the footing over. But in this case, a very astute fabricator had substituted larger anchor rods than the engineer had specified. He just thought they looked too small, and of course, the result was the footing tipped over. And I did talk to the engineer once, and there were claims against him in the beginning for not having a large enough footing, but I think that finally went away. So that's another kind of a unique situation. One of the things that occurs quite often are anchor rods that are too short. You can see in this picture one looks kind of too long, and one looks rather short. It looks like the nut is barely on the anchor rod itself. One of the things you should be aware of, if the one that's too long, you might question, is it buried deep enough in the concrete that you had specified? So if they're too short, there's lots of things you could do. You could extend the anchor rod by welding on a threaded rod to the anchor rod. You can use a coupling nut. You may have to cut some rods off. You may have to drill and use epoxy anchors. You might be able to weld the base plate to the rods. And then I put in parentheses, and I say it several times throughout this presentation, remember that you cannot weld to high-strength rods, those that are 105 KSI anchor rods. You can also perform an analysis to see if the nut is not all the way on, but let's say it's 3/4 of the way. Are there enough threads engaged to do the job? Because, like I said earlier, you have to know the purpose of the anchor rods, and if it's just for temporary erection, then that certainly would be a permissible thing to do. How to prevent this situation? Well, we're showing it because you can't always prevent things, but make sure you provide a design with ample length and ample thread length. Standardize the best you can elevations of anchor rods, and make sure your plans flag special conditions, because the person setting the anchor rods will get used to one detail and maybe forget any special situations, and that's when you run into problems. As I stated, don't use high-strength anchor rods, 55 or 105 KSI. It's often better to use larger diameter rods, the 836, because then if welding is a solution, it's much easier to accomplish. Here's a detail of an anchor rod splice. This is, you can see the top of the concrete. Let me see if I get a pointer up here. Well, I'll do a highlighter. Here's the top of the concrete right here. And then, I advanced one, too many. There's the top of the concrete. And this is a chisel point coming down. This is a backer bar here. And that solution has been used successfully. Another detail is one where we would lap with a couple of plates, and maybe some concrete has to be chipped out of the way, but some fillet or flare bevel welds could be used to connect these plates to the anchor rods. There are coupling nuts that one can obtain. The next few slides show a few of these. I had one instance to look at a situation where anchor rods were too short and they needed a coupling nut fix. You can see this is a pretty thick, large base plate, and you can see that the hole for the anchor rods has been torched out to accommodate a coupling. If you look down on top of the base plate, you can see the anchor rod. You can see the new washer that's going to be used. And like I say, there's several types of coupling nuts you can use. I found this particular one on the World Wide Web, and it allows you to screw to the anchor rod and then put an extension without welding then onto the anchor rod. So that's a solution that can often be used. However, you do need to generally make the hole in the base plate much larger and have enough room to do that. Those were too short. Sometimes they're too long. This picture I took many years ago before the OSHA requirement of 4 anchor rods. And again, the thing that I'd be concerned about is the anchor rod deep enough into the foundation system, because depending on the length that it was detailed, maybe it hasn't been set properly. You can certainly provide washers if they're too long, kind of like a little pipe thing that was done in the previous slide. You can weld the rods to the base plate if sufficient thread length exists. Again, so long as they aren't the high-strength anchor rods. Or you might be able to thread the rod in place to run a nut down. Prevention, make sure your details have plenty of extra threads on the anchor rods. And again, check for proper embedment if they are too long. I pulled this off a set of drawings that I had, and it's not as clear as I would like it to be, but there's a couple of things. I'm going to change this pointer here. You can see these have a nut on the base here, and what we always did is we would specify the length of the top of the nut to top of foundation because we need a certain projection. And then adding on to that, you've got the grout, the base plate thickness, the nut, of course, and some extra threads. So we would provide a dimension here and the dimension here. So besides giving the diameter and the strength of the anchor rod, it's nice to have a little drawing like this to let the contractor know proper elevations. So often, besides too long, too short, anchor rods are not always like you'd like to see them in a base plate. These are bent rather far over. This happened in the normal or northern climate where the base plate was covered with snow and the bulldozer ran over it and bent the rods, which wasn't a very good thing. Often you can cold bend A36 rods back to being straight. You might also be able to heat them and straighten them. Again, A36 material. If they're high-strength anchor rods, you probably can't bend them back because there's not enough ductility to keep from cracking them. So again, I recommend, if at all possible, not to use the high-strength rods. You're better off using bigger diameter 36 KSI rods. And certainly there should be protection provided for the rods during construction. What happens if the anchor rod pattern is rotated 90 degrees? That has certainly happened many times. Lots of the same solutions may be necessary that we just talked about. One thing you can do is make the pattern the same in both directions. That way, the column can be rotated the wrong way, but it's much easier to fix than the alternative. So you also may want to require special inspection for critical settings for the anchor rods. It reminds me of one story where we probably should have provided for a special inspection because the anchor rods were 12 inches in diameter and buried 12 feet deep into concrete. And of all the anchor rods on the job, it was for a mill stand. They were put in the wrong place. So it was a very expensive fix, but it got solved. Again, with anchor rods in the wrong position, you can see that here the erector took some real action and burned out part of the flange of the column. It turns out, in this particular case, that we evaluated the column and its strength, and even with the reduced section, it was not a problem. The anchor rods themselves were primarily there for erection, although there is a brace back in here, but those anchor rods were okay, so we left it as is. Again, for thinking about anchor rods in the wrong position, this was an interesting project where the detailer showed the distance on the setting plate incorrectly. It was supposed to be a setting plate that would accommodate the anchor rods as they are shown outside of the setting plate. So what happened was the anchor rods had to be burned off and new ones drilled in, and it was a fairly expensive situation. So you can see here where they're burned off. There were, by the way, there were 1,300 anchor rods on this project that had to be redone. So what are some of the solutions? We've talked about some of them. Evaluate the need for anchor rods. Cut the rods and use epoxy anchors if required. You might cut the base plate and use plate washers. You might on occasion have to fabricate a new base plate. Might have to modify the column web or flange as required. You might have to bend the rods into position, and that may of course cause you to chip away some concrete to be able to do that. From a prevention point of view, we say use a qualified field engineer. It wouldn't have to be a registered surveyor, but a good field engineer to lay out the anchor rods. We often say to survey the location of the rods before column fabrication. That's, as you know, it's kind of a joke in the sense that with all the fast track things we do today, quite often that is not done. But you make sure you use AISC recommended hole sizes, use symmetric patterns for the anchor rods, and use wood or steel templates. And the key word here is firmly fastened to the footing or piers so that you have the correct location of the rods. This picture just shows a condition where anchor rods are in place and the column had to be modified and then welded to the plate as shown here. You can see here was the original flange, and this is the new column, but so it was left in place. Again, I don't know why these were put in the wrong place, but they were, and I don't like the fact that there were so many. I would have thought that the engineer might use fewer anchor rods. One of the other things that happens, base plates can punch through leveling nuts. What's the solution to that? Well, generally it's to jack the column up and grout it. Prevention, use large, thick washers when using leveling nuts so that they don't punch through. Specify proper grouting time in your specifications. And for heavier loads, it's probably better to use a shim stock or setting plates instead of leveling nuts when you have the large loads. So those are, again, things that can happen. Let's discuss for just a moment what the proper specification for anchor rods is. I think most of you know this today, but anchor rods are controlled by ASTM F1554. And there are two items of interest on 1554. They relate to classification and also product marking, and that's color-coded. The A36 rods are supposed to be color-coded and shown in blue, 55 yellow, and 105 red. The 55 rods can be obtained in diameters up to 4 inches, and the 105 rods can be obtained up to 3 inches in diameter. Also, the 55, you can ask for what's called supplement S1 to require that the material is such that it is weldable. I mentioned earlier the recommended anchor rod hole and washer size. This is straight out of the Table 14-2 of the 15th edition of the AISC manual. And you can see for the anchor rod diameter given, the hole diameter, minimum washer dimensions, and then the minimum washer thickness. So that's right out of AISC, and I recommend that you use those particular hole diameters. Make sure that you use F1554 material. Use grade 36 where possible, and rather than high-strength anchor rods, use larger diameter A36 rods. Use a symmetrical pattern if possible. Use heavy hex nuts. Coordinate anchor rods and reinforcing steel. Especially, what I mean here is if you have a condition with a pier and you have several anchor rods, things can get quite congested. So make sure things are drawn to scale so that you know whether or not the anchor rods can actually be positioned properly into the pier. And don't use piers that are too short, which don't allow for the development of the anchor rods. A lot of the calculations for this are addressed in AISC's Design Guide 1. Some more information on details. Provide adequate grout thickness, usually at least 2 inches. You can use setting nuts for lightly loaded columns, steel shims for heavily loaded columns. Consider setting plates where grouting may be difficult. And you can often solve some nice problems using epoxy anchors for fast track jobs and complex layouts. And again, consider construction sequencing when laying out the pattern. Remember that OSHA 1926.755 has the requirements of a minimum of 4 anchor rods, and then the information about an iron worker with his equipment being 300 pounds and 18 inches eccentric from any column face. To me, it's sort of a phony thing in that the requirements on the anchor rods are so minor for that 300 pounds at 18 inches. I think a lot of erectors get a false sense of safety in that they think that the anchor rods can adequately prevent the partly erected steel from falling over and under wind, but it's not true. Those have to be evaluated. OSHA says that you can't repair unless you get the approval of the structural engineer of record, and approval must state how you're going to do the repair or how you're going to guide the column if it only has 2 anchor rods. And lastly, the contractor shall provide written notification to the erector of any repair or modification that he or she may do. So I spent, almost a half an hour on anchor rods, and again, it's because it happens so frequently. I wish we could get rid of problems with anchor rods, but I'm not sure we ever will. So let's now discuss some columns and beams, and some requirements for repair of them. This is a funny looking column, of course. It was in a steel mill in the scrap yard, and the columns and crane runways in scrap yards are magnetic cranes generally. They are used and abused the building significantly. In fact, AISE says that when you have a Class E magnet crane, the lateral thrust that you must design for is 100% of the lifted load. Well, this particular column had been reinforced once. It had been hit many, many times, as you can see, with the magnet, and did some nice damage to it. But hey, it's still standing up there. Steel is, what's our motto? Stronger and smarter. So it stayed up. One of the things that happens fairly frequently is the column is not plumb per AISC Code of Standard Practice tolerances. So what you have to find out is it out of plumb? And if it's out of plumb, what can you do? And it depends on the situation, but you can remove or adjust connections often. You might have to cut the anchor rods and move the column and replace the anchor rods with epoxy rods. Or if it is not objectionable to the owner, that he can visually see that a column is slightly out of plumb, you can leave it as is and then use the equations in the AISC specification, Appendix 6, to determine what bracing forces are required to keep the column stable. Remember, the AISC tolerances of H/500 for a column, that's anticipated, and the column equations are actually take that into consideration. So if it's worse than that, the out of plumbness, then you can brace the column using, like I say, Appendix 6 equations. Erector should check anchor rods and plumb columns in a timely manner. Another thing that happens is after erection, the beam line is too short, which causes out of plumb columns at some locations. And I only indicate here that weld shrinkage can cause shortening of approximately 1/8 inch in most CJP welds. And what do you do in that case? You may have to cut some loose and correct by weld build out or some other means to get the proper plumbness of the columns. That usually happens in very long lines of columns. Prevention: provide adjustable erection connections and plan welding to compensate for shrinkage effects. If after erection the beam line is too short or too long, and this can happen with moment end plate connections, if things have gotten too long, you may have to remove a beam. You may have to refabricate the end plate. You may have to shorten it up. If it's too short, you might be just simply a matter of providing finger shims to push the columns out to get the proper tolerances. Prevention: you should detail end plates short, approximately 1/8 inch on each end, to allow for A6 and fabrication tolerances. So those are a few things that happen with beam lines and columns that I've encountered through the years. Another item which comes up on occasion is camber problems in primarily multi-story projects. And so you got to think about what members you should camber if they need it. Certainly filler beams are often cambered, the girder beams, the composite floor beams, and trusses. So those are the members that are often cambered. you might call me a bit of an ironmonger at times if you don't need too much camber, and quite often I think you're better off just selecting heavier beams and not being so worried about camber. But anyway, these are the ones that you should camber. Members not to camber. Spandrel beams, those supporting fascia materials. Connections become very difficult. You don't want to camber continuous beams with cantilevers. That would be like beams that you're going to run over the top of the column. And certainly if you camber the beam, then you have to adjust the cantilever, and it's a mess. You don't want to camber beams with moment connections or bracing connections. It makes the connection detailing very difficult and will cause problems. You don't camber members with non-uniform cross-sections or beams with significant non-symmetrical loading. It's a good idea not to try to camber those. You also should not camber beams that are subject to torsional loads. Beams less than 25 feet in length, and this is general, 20 to 25 feet, you don't want to camber because they don't have enough grip in the cambering machine to do the job. So it's very difficult. Just use a heavier member. You don't want to camber beams with webs of 1/4 inch or less, because the bending of them will likely cause the webs to buckle. And same thing true if your flanges were very thin. You don't want to camber something that requires less than 3/4 of an inch. And generally we do not camber runway girders. They're just heavy enough that they don't need it, and it doesn't help. So you might ask then, okay, we can camber, but what is too much camber? Well, some of the solutions are to place the concrete to constant elevation. You might be able to, if you found out in time, you could remove the camber in the shop. You might have to replace some beams. Usually it's a concrete situation. One of the things I found, if the design was in accordance with ASD specifications, quite often if you look at the LRFD solution, you can put more concrete on and not exceed the requirements of the beam because of the differences in load factors between dead load and live load. So that is the first thing I always look at. Prevention, check the camber in the shop, make sure it's proper. Specify camber based on the concrete placement method. Under camber for constant elevation and full camber for constant thickness applications. If there's not enough camber, again, check the design for additional concrete required. You might provide shoring. Again, check the camber in the shop and design camber properly, or use stiffer beams. Some cautions to think about. One of the things you should consider is not to require as much camber for the beams at column lines as compared to like filler beams, because the added connection restraint at columns will not allow as much of the camber to come out when the concrete is poured. So also be very careful of camber differences between beams and open web steel joists. You can check with the SJI requirements on joist camber, and what you don't want is some major differences with adjacent beams and joists, for example, where the cambers are not compatible. Also be careful of cambered beams or joists adjacent to non-cambered moment frames or frames at the walls. I learned very early in my career about camber of deep, long span joists on a building where it was a hockey rink. I think it was 200-foot clear span. And I had a joist next to a masonry wall. And of course, when it was set, it was roughly 6 inches above the height of the wall because I hadn't thought about the camber. So we all make mistakes. That was one of my early mistakes. I have more, but I don't want to tell about all the mistakes I've made. Some of the camber tolerances. From the AISC Code of Standard Practice, section 6.4.4, it says, for beams greater than 50 feet in length, the camber tolerance is -0 plus a ½ inch, with an additional 1/8 inch for each additional 10 foot in length or fraction thereof beyond the 50 feet. The AISC Code of Standard Practice specifies that camber is measured in the unstressed position in the shop. You cannot measure camber once it's on the job site. If you want to check on camber, you do it in the fabricator's shop. And what to do about extra concrete due to beam deflection during concreting? Solution, as I mentioned earlier, reevaluate the beam strength to determine if it can support the additional weight, or you may have to reinforce some members. Prevention, you can design beams as though they're going to get extra concrete, and I think that's a very good solution because we know quite often that is going to happen, and I think in our specifications, we always allowed for about 10% more thickness than what the drawings called for, because we know that depending on how they screed, you may get extra concrete. So it's a lot easier to have a little extra steel than to be worried about some overstressed member. Provide notes on your drawings of the need for the extra concrete. That way there'll be less arguments about, oh, hey, the engineer didn't give me a strong enough beam because it deflected too much, and you should have expected that there's extra concrete. So put notes on your drawings that there probably will need, depending on how it's screed, extra concrete. You can provide a little more camber. But again, you could use stiffer beams. A few comments now about shear studs. What if shear studs break off during inspection? I think the way most people check shear studs are they put two studs in, and then they bend them over at least 30 degrees and inspect. And they should bend over without the welds breaking. They should bend over about 30 degrees. People just take a sledgehammer and they knock them over, and if they're welded properly, they'll stay intact. If there's only a few that might break, you can certainly fillet weld the studs in place. But if there's very many, you don't want to do that. So to prevent that problem, they got to be installed properly. The stud gun has to be calibrated properly. And you can refer to AWS section 7.6 for qualification requirements. Sometimes studs are too high. And this is found out, hopefully, before the concrete's placed. You can remove the studs and replace them. Again, you can use additional concrete thickness. The reduced beam camber by heat straightening. All those are expensive solutions, certainly. But if they're too high, they're too high. Prevention: specify camber properly, or not at all. Don't use composite beams. That's a solution. And again, I've seen people use composite beams where they're short spans, and it just doesn't make sense to make them composite. Just forget the studs. And also, you could design with some added capacity to prevent things. So if you need more concrete, you can get away with a little more concrete on the beams. A few comments now about fit-up problems. The ones that I've seen most frequently are fit-up of weak axis moment connections, and I even hate to show this slide because it's a darn shame that we have a moment connection going into the weak axis of a wide flange shape. They're not rolled to have weak axis moment connections. You're far better off turning some columns in your framing situation rather than to create weak axis moments. But enough about that. If it does happen, quite often there's misalignment between the continuity plates and the beam flange, and this usually occurs when the continuity plate is the same thickness as the beam flange. This particular slide shows that situation. The beam coming into the continuity plates doesn't hit the continuity plates exactly, and resulting in weld problems. This is all due to not the fact that maybe they were detailed incorrectly, in the sense that the detailer and engineers need to recognize the ASTM A6 tolerances on beams. And I'll show a slide in just a moment on those. Because otherwise this situation can occur. What you should do is make sure that your continuity plates that you're framing into are thicker than the flanges of the beam. We show here upper flange stiffener detailed 1/4 inch greater than the beam flange thickness, and the lower one 3/8 greater. So they're bigger, but again, it's just material. That's not the big problem. If you can't get a proper weld there, you're going to spend a lot more money than having to provide a thicker continuity plate. The situation also occurs in conditions where you might have a bolted flange plate connection to the, in this case, the strong axis of a column. You can see the gap here and here, and in this case the erector tried to pull the plates together partially successfully. This also happened to me once on a project where we had W36 beams and very large columns with wing plates like these. And unfortunately, the columns were fabricated by one fabricator and the beams by another, and so no check was made on the overrun of the beams, and this would cause a problem. What you can do is provide some areas for shims in a detail like this, both at the upper and lower wing plates. When I talk about A36 tolerances, this is out of the AISC manual, table 1-22, and it shows what you can get from the mill. Things are not perfect in this world. In fact, if we look here, let's take a beam with a nominal depth of something over 12 inches, and you can see that, let's see, the maximum C distance, that's this one, that's the depth, can be over the theoretical depth by as much as 1/4 of an inch. So if those things have been detailed just right on, you're going to have a situation like the previous slide. Some of the solutions to this problem are certainly to jack against the beam by snugging bolts and then tensioning. And using shims, as I mentioned. If the beam does not fit between the plates, that's what I had to do on the big W36 I had. I had to remove the top plate and then re-weld it to the columns. Provide the shim space, check your A6 tolerances, modify the weld detail and weld sequence to reduce out-of-plane distortion. That can happen from the welding to the column. And heat straightening may be required after welding. Another question that comes up on fixing, and it's not really a field fix, but can welding to embeds damage the concrete? And yeah, too much heat can cause concrete spalling. However, I've seldom seen this as a problem unless somebody is really calling for very large CJP welds from a beam into a embed plate. To prevent too much heat, I would suggest using fillet welds, looking at a proper weld sequence, and provide thick enough embed plates. By being thick, they'll dissipate the heat. They have nice heat sink. As a rule of thumb, use a 1/2 inch minimum thickness for deck bearing situations, and at least 3/4 inches for beam bearing. And I think you also know that there is no such thing as an embed plate being too big, because they are often mislocated, and just make sure you specify them considerably larger in width and length or height than you need, because if they're off by a few inches, you want to be able to properly connect to them. Okay, a few comments now about some interference problems. This is a cute picture. I don't know the history of this condition, except that obviously there were a couple of pipes and a beam brought in, and pipes were in the way, and some radical web openings were used to accommodate the pipes. It almost looks like somebody was also trying to create continuity. It looks to me like there's all sorts of welding up here and down here, but things didn't quite line up. This one I do know about. This building collapsed, but further downstream. But it was the same column as the one shown here. At some point, obviously there were some pipes coming in, and by golly, one opening was pretty severe, and it buckled on the frame line 1 or 2 bays down. That's just abuse, which you do find it in some of the industrial applications. You don't find it that often, of course, in multi-story projects. But in some of the industrial applications, you find some crazy things that we can blame on the owner. I'm sure a fabricator didn't do that. I'm sure an erector wouldn't do that. Again, this was one I saw. Pipe interference. His pipe was in the way. So, of course, the flange and part of the web was cut out so the pipe could be set down in there. And then a very, very nice splice was made here to keep the continuity. And yes, it was in the compression area, but it was at mid-span. I don't think if fully loaded, it would work very well. Also, one of my favorite pictures is shown here. There was, who's ever there last gets to do whatever they want to do to the structural steel, and here they made it fit okay. I think I do have time for a cute story that I believe to be true, and that is. There was a project, and I believe it was in Texas, where it was a series of open web steel joists framing into a beam line, and the HVAC contractor came along, and he was going to put his ductwork right adjacent to the steel beam. So, of course, the end diagonals of the joists were in the way. So he cut all of them. I think there were like 30 joists. Cut the end diagonals and put his nice rectangular duct in. And then called the joist manufacturer and said, you have a problem with your joists out here. Well, normally there would be a heated discussion, which there may have been, but the joist manufacturer was a pretty savvy guy, and he went out to the job site, and he torched holes in the HVAC and stuck his end diagonals back in and re-welded them, and called the HVAC contractor and said, oh, by the way, your duct is whistling out there. It has some sort of problem. So they both deserved what they got. So that's a true story. This interference problem also I'm aware of because it was a building that I designed, and I went to the job site, and there was a liner panel everywhere except this one location. The liner panel had not been put in, and the rods were interfering with the girt system. I'm sure that under a nice wind pressure that girt wasn't going to work very well. I had the erector take down the liner panels at locations where bracing was located, and in every instance it was the same thing. There was no attempt made to even scab a new flange on the girt system. I don't know, partly my fault, I guess, for not recognizing that the bracing would interfere with the girt. However, I would have thought common sense, which is sometimes stupid to think about, that the erector might have torched a little hole in the web and threaded the rods through there, which wouldn't have been much of a problem. But so I made him reinforce all these situations. And speaking of reinforcing, lots of ways to do it, and each one depends on the situation at hand. And these are just some sketches that have been used successfully on projects when you need more strength and or stiffness. The added plates, some of these, obviously, if there's a concrete or something up here, you can't get a downhand weld to these. You might actually use this condition up here as well. You can put that in there like that and like that. Makes a very torsionally stable beam, but you could get to the welds if you can't get a downhand fillet weld up at the top. Sometimes you can actually scab a new beam onto the existing beam if you need extra strength. Copper plates are the normal thing that you think about. Again, it's the best solution, but whether you can make this weld is something to think about. This one is similar to those plates I showed. Provides lots of lateral stability to the beam and does work, as does the one here. There is a AISC educational document, Design of Reinforcement for Steel Members, Part 1 and 2, that you can look at by going to www.aisc.org/education archives. So you should be aware of that. It's just ideas. You know, any idea you come up with, if you design it correctly, is going to be a good idea. So reinforcing connections, solutions, it's wide open. I mean, it depends so much on the situation at hand. You can remove and replace the connection with a stronger one, obviously. Sometimes you might be able to use X bolts instead of the threads being included in the shear planes. That may solve the problem. You can add weld length or increase weld size many times. Depending on the condition, maybe it's an old riveted job, you can remove old rivets or A307 bolts and replace them with 325s or 490s. You can ream holes and use larger diameter bolts. And you can add web framing angles to a seated connection, or you can add a seat to a web frame connection. So it depends on the situation, obviously, but again, I think if you just use your head and design the reinforcement properly, you can solve a great number of problems. Again, some other solutions, you can add weld to existing riveted or A307 bolted connections. You have to make sure that it's a weldable steel that you're dealing with. Add weld to existing high-strength bolted connections. You can do that. I refer you to AISC J1.8 and 1.9. You can extend the length of framing angles by welding on additional length if there's additional length to be had. And you can sometimes add a second angle to a single angle connection. So again, use your head and design it. So more on some fit up. What if the bolts don't fit in the holes? Let's think about shear connections for a moment. The AISC specification section J1.8 permits load sharing between welds and bolts when 4 conditions are met. I'm not going to go over those, but I encourage you to look at J1.8 for the details when you can share welds and bolts. For welded alterations to structures with existing rivets or bolts, section J1.9 permits load sharing when certain conditions are met. One of which is that the weld available strength must not be less than 25% of the required strength of the connection. And that's usually easily satisfied. The condition that I'm showing here was I probably shouldn't say where it was, but it was a bad situation. You can see that these holes aren't lining up with any holes in the member beyond. It's a big, heavy bracing connection. So it's just fit-up problems. Shouldn't happen, but it did. Here's another shot of a different one of the connections, and you can see obviously that the bolts don't fit in the holes. So not nice. What if they don't fit? Well, so you can ream the holes within reason, of course, and you can go to the specifications for your maximum oversized hole, for example. You can field weld. You can fill some holes and re-drill, and you can replace connection material. All depends on the situation. And prevention is, I say, easy. By proper detailing and proper fabrication, it should not happen. If there are some tricky situations, quite often it's nice to design using slip-critical bolts and oversized holes. That gives a little leeway on fit-up. What is too much reaming? RCSC specifies a 32nd inch each ply, but notes research that larger holes can be permitted without reducing bolt shear. Holes can be reamed to diameters up to and including the oversized hole diameters as shown in AISC Spec Table J3.3. And one of the main things to check, depending again on what the connection's doing, is edge distances. Make sure that they are permissible after reaming. If you have insufficient edge distances, you can perform an analysis to see what the strength is. You might have to add material to increase the edge distance. A good way to prevent these things from happening are to not design connections with minimum edge distances too tight. Keep out of trouble. I think if you always add an extra 1/8 inch to edge distances, in most cases, if reaming has to be done, you won't create a bad situation with the edge distance. Let's talk for a few minutes about the member selection guidelines. A good guideline is to use deeper floor framing members when large copes might be necessary, depending on what you're framing into. You don't want to create a situation where a very large cope is needed on your filler beams. Actually, you don't want copes at all if you can prevent it by proper detailing with proper connections. So think about how the members are coming together and whether or not size of the cope that might be necessary. You know, I often, when I look back and remember talking to some of the young engineers saying, I think the first thing, well, not the very first thing you should do, but one of the early things you should do before you select your member sizes is to think about what kind of connections you're going to use. And it's the type of connection that may control the size of your members. And an example, of course, would be in a truss where if it's going to be field bolted splice, you want to make sure that the member's big enough so that when the holes are punched in the flange or the web of the members, you still have enough net section to carry the load. So there's all sorts of things that the engineer should think about, I think, when he's selecting the members. And I think I have a couple of minutes. I'll go off on another tangent, and that is the use of the computer. I see too many times, well, today I hear the folks say it's all about the model. And true, modeling is wonderful. But when running an analysis on the computer, I think what should be done is, rather than letting RamSteel or any of the programs just designed for the 120 different load combinations and then picking your members, I think it's really a good idea to run just the 2 or 3 load combinations that you think are going to control a design. And in most cases, it's dead plus live and dead plus wind and dead plus live plus wind. And so then look at your answers. Does everything make sense? And once it makes sense, then, okay, press the button and let it go through all the various ASCE 7 god-awful load combinations. When I say god-awful, I have a friend in Chicago that told me they had one building where they had 804 load combinations. So I'm sure they just gave the computer output to the fabricator and said, here, design these. But no, I get off my stump there. But it's important to look at what you're doing before you select your members. Avoid beams with 4-inch flanges. These are spandrel beams. Beams require bolting flange connections, double joist bearing. You need more than 4 inches. With composite beams, limit deflection to avoid large cambers. Use minimum % of composite to limit the studs. And avoid studs on infill beams parallel to the deck ribs. Depending on how they lay out the deck, it may be an ugly sight if you have a high rib right over your infill beam. Show the reactions on framing plans. And use standard AISC details, double angles, single plates, end plates, and show special connections on your plans. You may want to provide the actual moment envelope if you're not designing the connections. Some design considerations: end plates may be limited by bolts or column flange bending capacity. They may or may not be the right solution. CJP welds are so easy to specify, but generally very expensive, so do a little thought before you ask for a CJP weld. Top and bottom bolted plates are an option if less than MP is required. And AISC used to talk about clean columns, but size the column to avoid reinforcement. Pick a bigger column to eliminate doubler plates in particular. Get a column with a thick enough web where you don't need a doubler plate. They're very expensive to fabricate. Some thoughts on cantilever design guidelines. Again, provide the actual moment and shear forces. Indicate if camber is required. Use end plate connections where possible for erection ease and safety. Shop weld on short cantilevers where possible to avoid having to do those in the field. And consider making the beam continuous, that is, stacking it up on top of the columns for if you have long cantilever situations. It's a better way to do it. A few bracing connection guidelines. Show all forces, including transfer forces. You've all heard of these things, but sometimes we forget. This is a good one. Consider modifying work points for extreme connection geometry. If you have a big truss, for example, framing into a column flange, you may want to make the work point be at the flange to reduce the size of gusset plates. If you take it to the center of the column, fine, but it can cause some much larger connections. Yes, if you go to the work point at the flange, you may have to increase your size of the column, maybe one size because of some extra moment, but it's probably cheaper in the long run. And allow oversized holes in field welding. Now I guess I should say that's the formal end of the presentation. The next series of slides I want to show you, I have shown in talks many, many times, and if you've seen them before, fine, take a nap. If you haven't, or even if you have, there's always something a little different that you might pick up from these slides. And Brent Liu always wants me to show these slides because they are such a nice story. So I've called this the classic overhead crane building. As some of you may know, I spent most of my career in the industrial building world and designing crane buildings and looking at various crane buildings and problems thereof. This particular building that I'm going to show you, I worked with the owner on several projects. We got to know each other quite well. We got to know the games that, I think they were games that he played, and I subsequently played games because the first project I did, I went into him and gave him the price, and he said, oh my God, he said, that's way too expensive for what you're doing. And I said, well, you know, I really want the job, Lou. And he said, well, you're going to have to take some money out. So, not that I liked it very much, but I did take some money out, and I got the job. I figured out that's going to be his hot button. So the next job, I inflated the price by about 30%. And went into him, oh God, that's way too much. I said, well, okay, Lou, what do you want me to do it for? Well, got it down to the price I wanted. And this went on for years. And I think he knew what was happening, but I think he also thought, I'm doing my job for the owner in getting the right fee. So anyway, we had a great time. So the particular job I'm going to show you, he called me and said, I have this crane building that is an absolute disaster. We can't run the cranes in it. It was designed as an automatic crane rack building and computer controlled, and the building just moves way too much. So the computers can't even control where to fetch the materials. And he said, Jim, I think you ought to design this building for me for free, or do the fix for free. I said, Lou, I'm not going to do it for free. I'll do it for time and expense, which is the way you got to do fixing up jobs, of course. And he finally said, okay. So anyway, I went into this building. And the crane runway, the first thing I see, of course, is a nice crack here. And I also see that something's been torched off here and torched off here. Originally, there was a tieback that went from column flange over to here, and it cracked because the girders were designed as continuous girders. In fact, you can see that a weld crack happened right along here due to fatigue. And so somebody cut this off, realizing that the girder could not rotate properly at the column, and put in these heavy angles, at which point they fractured at some point in time. Somebody tried to fill them in with weld. So the tieback system was a disaster. And most fatigue problems that I've witnessed in crane buildings do occur at the tieback location. Here's another one, and here again it had been cut off, and somebody put some nice little plates on here thinking they might work. They must have broke because they reinforced with something here. Now the thing to know, again, notice that this weld has cracked all the way across the girder. But notice how nice and shiny this runway rail is. And notice all the stuff on the top of the runway channel cap. That's metal, and it's metal off of the crane rail. And this occurs when a crane is misaligned and it goes up and down the runway and gulls into the rail and chews it up. And this building was suffering from total misalignment, and the building was moving around, and like I say, they couldn't use it as intended. One of the problems was that the building at one point in time was filled with pigeons. And you don't have to believe this story if you don't want to, but I think it's true. The little pigeons would poop on the crane rails. And when the owner would, or the crane operator would go to put on the brakes of the crane, the stuff was real slippery, and the wheels would slide, but on the adjacent runway, if they hadn't pooped right there, the rail would bind up, the wheels would bind up because the brakes are on. The other one slips and slides, and it racks the crane. So the owner put this yellow goop on his girt system, and the poor little pigeons would come and they would stick to it, and then of course he'd take the pigeons, and I'm sure he took them out into the woods somewhere and gave them a nice safe home, but he got them out of his crane building. Now when a crane gets misaligned, you can see the crane stop here. What the operators will do is they'll start at one end of the runway and they'll ram the crane into the stops to take the skew out. And you can see that had been done a few times here. You can see it's been ripped away from the channel cap. And that's because they were just ramming this crane in to straighten it because, again, the building is moving far too much. Now, some engineer came along and thought, he'd stiffen these columns. I can't say this was an engineer. I'm sorry. Somebody came along and said, okay, if we put these straps on some of these columns that were sort of truss-type columns, and we anchor rod those into the side here, and then we attach it, it's going to stiffen up those columns laterally, and we'll have a much stiffer building. In addition, somebody, you can see what a gobbled up mess this is, tried to stiffen some columns by adding some struts on. Looks like they welded some braces in here too, in there too. So when all else fails to laterally stiffen the building, then what you do is you lean it on the building next door. And fortunately, the owner owned that building as well. But this is a fine piece of engineering. You can see the slenderness ratio of these beams are taken care of by these nice pipe struts, both strong axis or weak axis and strong axis. And believe it or not, that did work. And this is a brick building, but they were tied into some steel over here. So that's my favorite slides. I'll probably never show these again, but so you may have the final seeing of those. I would like to give contribution to my friend Larry Kloiber, who helped with the presentation in the past. He's with Lejeune Steel. And my friend Tom Farrell from Farrell Engineering that gave me some details. And also the AISC Solution Center gave me that picture of the wing plates on the beam that didn't fit. So are there any questions?
All right, thank you, Jim. And your guess is correct. We do have questions from the audience, and Before we get to that, though, I know we're tight on time, everybody. We're going to do our polling questions. We'll get to one tonight, just one. So here's our first polling question, first and only polling question for the evening. True or false? It is permissible to heat bend an ASTM F1554 grade 105 anchor rod. Go ahead and choose the answer you think is correct by clicking on the radio button. Again, question is true or false. It is permissible to heat bend an ASTM F1554 grade 105 anchor rod. Last chance. All right, I'm going to close the poll. Wow, Jim.
Yeah?
Good. 94% chose false. What do you think?
I'm worried about the 6% that said true. So the answer is false.
Okay, I think everyone was paying attention on that one. All right, we're just going to do one due to the time constraints this evening. All right, with the time we have left, Jim, we had several questions on anchor rods, so let's get to those. So can you see the slide I'm on? I'm on slide 23, Jim. Can you see that?
Yes, Bradley.
Okay. Yeah, so the question is, do you get concerned at all about these excessively or irregularly cut holes and how they might affect the performance of the base plate?
No. Unless, we're concerned about some sort of repeated load condition where a notch might affect the material or the condition. No, I'm not concerned. It would depend on like a fatigue problem. So generally, no, I would not be that concerned. I know we all say in our specs you can't do it, but sometimes it's the lesser of many evils.
Okay. I'm going to go to slide 37, I think. No, let's go to 35. There's a comment from one person, question from another person about anchor rods being placed during concrete placement. The comment is, many times the anchor rods problems arise because they're set by the concrete contractor and not the erector. They tend to move with the progress of concrete placement. And the question is, how are they held in place when the concrete's being placed? And maybe another question is, how do you minimize the issues with anchor rods starting out in the wrong position during the concrete placement?
Yeah, I think I stressed that a setting plate or a pattern, either wood or steel, should be used, and it should be, I think I used the word, firmly anchored to the formwork in some manner so that when the concrete is placed, it doesn't shift around. And yeah, it's hard to do, but quite often, it's a couple of 2x4s is all it takes, spanning across to the edge of the foundation system, and the template securely fastened to that. To keep it from moving is the whole key. So that's what should be stressed.
Okay, then moving on to slide 37. The use of leveling nuts, is that typical, or is there certain situations where you'd see leveling nuts used?
I see leveling nuts used on maybe one-story, possibly two-story buildings where the loads are pretty light, and they can adjust the height of the base plate easily with the leveling nuts. But as I indicated, if the loads get heavier, then the shim stacks are probably a better way to go, because you don't want to punch through the leveling nuts. If you're going to use leveling nuts, you should have a thick enough washer so for whatever load's going on there, it doesn't do like a punching shear problem on the base plate, or on the washer, sorry.
Okay. All right. And then for column base plates that are set on shim packs at erection, should the shim packs be removed or left in place?
I think you can just leave them in place. I don't see any reason why they would have to be removed.
Okay. I should have the slide up here. I'm sorry I don't. The requirement for 4 anchor rods minimum. The question is there differentiation made in defining a column versus a post?
I don't think OSHA does. I'd have to recheck it, but I think they say, you know, a post can have just 2 anchor rods. But I don't think they really declare, and I could be wrong, what's a post and what's a column. To me, a post would be a, you know, 1-story little post underneath a beam. But I'd have to check. I don't think they differentiate, but they do say that.
Okay. Maybe we can follow up on that one. Okay. And then I'm going to jump back again. A lot of questions on anchor rods. I'm going to jump back to slide 23 again, or maybe 22 even. So the question is, what number of exposed threads is considered a minimum for rods before they're too short?
The top of the rod should be at least flush with the top of the nut. In other words, the nut should be able to be put down far enough so that the top of the rod is flush with the top of the nut. If it's less than that, then you would have to evaluate, well, is there enough shear strength in the threads to do the job that you need?
All right. All right. A couple of questions on camber. Regarding too much camber, the question is, would you consider flame straightening in the field to correct an over-cambered beam? I
guess I would consider it, yes. Obviously, you need a person or persons that are knowledgeable in flame straightening so they don't screw things up worse than they are. But yeah, I think that is a potential solution. I've never encountered it. I've never had to do it, but I think it is something that can be done. Okay, and then on the same slide, looking for clarification about concrete placement. The question is, when is concrete not placed at a constant elevation? It depends on how the contractor sets up his screeds. And the best way to explain it is there's a lot that could be said about it, but I would refer to, there's an engineering journal article by John Ruddy, and it's probably 20 years old. But I think if the person goes to the EJ series and looks up John Ruddy, he had a very excellent article on placement and the ways to do it and what can happen. So I think that's the best way to answer that question. Okay. All right. Let's go to slide 85 now. All right. Your second bullet point here, avoid beams with 4-inch flanges. The question is, why couldn't you place the joist staggered to avoid requiring a larger flange? Yes, you can. It's just kind of a crazy layout, and it may affect well, if it's a floor, obviously, you know, the deck has to be coordinated with the offset joists. But yeah, you can do that. There's nothing wrong with that. It's just easier, I think, and simpler to have something with a 5-inch flange. Let's sell some steel, you know. But yes, the answer is yes. You can stagger the joists to accomplish that.
Very good. All right. Well, we are more than out of time, and I think we're going to wrap up for this evening. If your question did not get answered tonight, we will make sure we get a response from Dr. Fisher, and we'll get those answers sent out within the next week or so. Have a good night.